Greetings everyone, welcome to A&E Learning Hub, where I'm going to go through and explain the solutions for questions related to motors and generators. Alright, so before I begin, I'm going to ask that those of you who have not yet subscribed to the channel, please to do so, and to like the videos and share the videos with others, especially those who are doing Csec electrical. All right, so let's begin. So this is question 10 from the 2008 past paper. It says, figure 5 shows the diagram of a 4-pole DC motor. Part A, it says, in your answer booklet, write the numbers 1, 2, 3, 4, and 5. Beside each number, write the name of the corresponding part of the DC motor shown in figure 5. All right, so 1, that is the main field coil. 2, that's the armature. 3, that's the horseshoe. 4, that is the yoke. And 5, that's the commutator. All right, so that's it for part A. For part B, it says explain the main function of each part of the DC motor named in part A above. All right, so the field coil is used to produce the main magnetic field that interacts with the rotating magnetic field of the armature. Next up, we have the armature. So this is used to produce the rotating magnetic field that drives the motion of the motor. Next up, we have the horseshoe. This is used to distribute the magnetic flux to a wider surface area. For the yoke, this is used to house the internal parts of the motor. And finally, the commutator. This is used to convert AC current to DC current. All right, so that's it for part B. Part C, it says name 3 types of DC motor that are identified by the way the armature and the field windings are connected in the motor. All right, so the 3 types of DC motors are series motor, shunt motor, and a compound wound motor. That's it for part C. For part B, it says state 2 ways of achieving reversal of rotation in a DC motor. All right, so the 2 ways are 1, changing the polarity of the voltage to the field windings. 2, reversing the connection of the armature windings. All right, so that's it for part D, and that's it for that question. Let's move on to the next question. So this is question 3 from the 2008 past paper. Part A, it says state 2 methods of increasing the terminal voltage of a DC generator. So the 2 methods are 1, to increase the strength of the magnetic field. 2, to increase the speed at which the armature is cutting the magnetic lines of force. All right, so that's it for part A. Part B, it says name the field windings of a compound wound DC generator. So the windings are 1, series field windings. 2, shunt field windings. So that's it for part B. For part C, it says state 2 methods used to excite the magnetic field of a DC generator. So the 2 methods are 1, self-excitation. 2, separately excitation. D, it says state Lenz's law of electromagnetic induction. Lenz's law states that the direction of an induced EMF is such that it will always opposes the change that is causing it. All right, so that's it for this question. So let's move on to the next question. So this is question 8 from the 2012 past paper. It says figure 10 shows 3 DC motor connections labeled W, X, and Y. It says write down any 2 of the letters W, X, and Y and give the name of the connection by each letter. All right, so I have all 3 letters here and the name of the connection. So for W, that's the series wound motor. For X, that's the shunt wound motor. And for Y, that's the long shunt compound wound motor. All right, so that's it for part A. For part B, it says figure 11 below shows a motor circuit. Its parts are labeled 1, 2, 3, and 4. In your answer booklet, write the numbers 1, 2, 3, and 4. Beside each number, write the name of the part of the motor indicated. All right, so 1, that's the tapped resistor. 2, that is the series winding. And 3, that's the pot resistor. And 4, that's the armature. All right, so that's it for part B. For part C, it says a DC motor with voltage of 100 volt has an armature resistance of 0.2 ohm and an armature current of 20 ampere. Calculate the armature voltage drop. So armature voltage drop, which is VA, is equal to IA times RA. That is 20 ampere times 0.2 ohm, and that will give us 4 volt. All right, so that's for part 1. For part 2, it says to calculate the back EMF. So back EMF is equal to V minus IA times RA. So that is 100 volt minus in bracket 20 amp times 0.2 ohm. That will give us 100 volt minus 4 volt. So back EMF is equal to 96 volt. All right, so that's it for part 2. For part 3, it says to calculate the power loss in the armature. All right, so power loss is equal to the current square times the resistance. So that is equal to 20 amp square multiplied by 0.2 ohm. That will give us 400 ampere times 0.2 ohm. And that will give us a power loss of 80 watt. All right, so that's it for part 3. For part 4, it says to calculate the power supplied to the motor. All right, so P is equal to V times I. That is 100 volt times 20 amp. That will equal to 2000 watt. All right, so that's it for part 4. For part 5, it says calculate the electrical energy when the motor is in use for 20 hours. All right, so the first thing that we have to do is to calculate the total power. So the total power is equal to the power of the motor minus power loss. So that is 2000 minus 80 watt, and that will leave us with 1920 watt. All right, so the next thing that I did was to convert the total power to kilowatt, and we divide 1920 watt by 1000. That will give us 1.92 kilowatt. So to calculate the energy now, so that is the total watt multiplied by the number of hours, and that is 1.92 kilowatt multiplied by 20, and that will give us 38.4 kilowatt hour. All right, so that's the total amount of energy that is used by the motor for 20 hours. All right, so that's it for part 5, and that's it for this question. So for the next question, which is question 7 from the 2010 past paper. Part A, it says figure 2 shows a short wound direct current machine. For the armature resistance, RA is equal to 0.2 ohm, and terminal volts, VT, equal 200 volt. Part 1, it says calculate the generated EMF when the machine acts as a generator with the output current of 80 amp. So the generated EMF is equal to the terminal voltage plus IA times RA. So that is 200 volt plus in bracket 80 ampere times 0.2 ohm. That will give us 200 volt plus 16 volt. That will give us 216 volt. So this answer here should be 216, not 206. All right, so that's it for part one. For part two, it says the generated EMF when the machine acts as a motor with the input current of 60 amp. So the generated EMF is equal to the terminal voltage minus IA times RA. That is 200 volt minus in bracket 60 amp multiplied by 0.2 ohm. That will give us 200 volt minus 12 volt, and that will give us a generated EMF of 188 volts. All right, so that's it for part two. For part three, it says to calculate the mechanical power in watts developed by the armature when the machine acts as a motor. All right, so mechanical power is equal to the generated EMF multiplied by the current of the armature. All right, so P is equal to 188 volt multiplied by 60, and that will give us 11,280 watt. All right, so that's it for part three. Part B, it says what is the function of a variable resistor placed in the starter circuit when the machine acts as a motor. All right, so it is used to vary the resistance of the circuit, which in turn vary the current to change the speed of the motor. All right, so let's move on to part C. It says, explain briefly the function of the field resistor RT when the machine acts as a motor. The field resistor is used to increase the resistance of the shunt field. As a result, the shunt field current can be reduced, which in turn reduce the field flux. By doing this, the speed of the motor can be varied. All right, so that's it for part C, and that's it for this question. All right, so let's move on to the next question. All right, so this is question 6 from the 2013 past paper question. It says figure 6 and figure 7 shows single-phase electric motors. Part A, it says give one name for each type of single-phase electric motor shown in part 1, figure 6, part 2, figure 7. All right, so part 1 of A, figure 6, that is a split-phase motor. Part 2 of A, figure 7, that's a capacitor start, capacitor run motor. All right, so that's it for part A. Part B, it says on separate lines in your answer booklet, write the letters A, B, C, and D with reference to figure 6, and E, F, G, and H with reference to figure 7. Next to each letter, name the part of the motor identified by that letter in the diagrams of the motors. All right, so for figure 6, A is the centrifugal switch, B is the starting winding, C is the main winding, and D is the rotor. All right, so this is figure 6. So A, centrifugal switch, B, starting winding, C, main winding, and D, the rotor. All right, so for figure 7, E is the centrifugal switch, F is the running capacitor, G is the starting capacitor, and H is the starting winding. All right, so here is figure 7. So F is the running capacitor, E is the centrifugal switch, G is the starting capacitor, and H is the starting winding. All right, so that's it for part B. For part 1 of C, it says explain briefly the functions of the components F and G in figure 7. So F, the running capacitor. So this capacitor is used to enable the motor to run. G, the starting capacitor. So this is used to start the rotor of the motor. All right, so that's it for part 1 of C. For part 2, it says explain briefly a method that can be used to reverse the direction of rotation of a single-phase motor. So a single-phase motor can be reversed by changing the direction of the rotating magnetic field produced by the main and starting winding. All right, so that's it for part 2 of C, and that's it for this question. So let's move on to the next question. So this is question 4 from the 2006 past paper. Part A, it says give 2 methods used to reduce the starting current in 3-phase alternating current motor starters. So the 2 methods are 1, auto transformer, reduced voltage starter, and star delta, reduced voltage starter. All right, so that's it for part A. For part B, it says name 2 effects of an electric current that are the basis of constructing overcurrent protection devices in 3-phase motor starters. So the 2 effects are overload and phase failure. All right, so that's it for part B. Part C, it says figure 1 shows the schematic of a single-phase capacitor start induction motor. It says explain the function of the capacitor C and the switch S1. All right, so for the capacitor, so the capacitor will create a starting torque or phase difference between the auxiliary and the main winding that will cause the single-phase motor to start. All right, so for the centrifugal switch, the centrifugal switch is used to close the circuit of the starting winding, which is needed to start the motor. Once the motor comes up to its operating speed, the switch opens the starting winding circuit and the motor runs normally. All right, so that's it for part C, and that's it for this question. All right, so let's move on to the next question. All right, so this is question 7 from the 2003 past paper. Part A, it says name 2 types of 3-phase induction motors. So the 2 types of 3-phase induction motors are squirrel cage motor and wound rotor motor. So that's it for part A. For part B, it says explain the meaning of the following terms. Part 1, slip. So this is the difference between rotor speed and synchronous speed. Part 2, synchronous speed. So this is the speed of the rotating magnetic field. All right, so that's it for part B. For part C, it says at what stage of the inductor motor's operation is the supply frequency the same in the magnitude as the rotor frequency? All right, so that's at the starting of the inductor motor. All right, so that's it for part C. For part D, it says a 3-phase 4-pole induction motor operates from a 50 Hertz supply with a slip of 4%. It says calculate the following. Part 1, synchronous speed. So synchronous speed is equal to 120 times the frequency divided by the number of poles. So that is 120 times 50 divided by 4. That will give us 6,000 divided by 4. That will equal to 1,500 RPM. All right, so that's it for part 1. Part 2, it says to calculate the rotor speed. So slip percentage is equal to synchronous speed minus rotor speed divided by synchronous speed. So therefore, rotor speed is equal to 1 divided by slip percentage. And that will give us 1 divided by 0.04 equal to 25 RPM. All right, so that's it for part D. For part E, it says figure 3 shows the schematic diagram of a motor starter. In your answer booklet, write the numbers 1, 2, 4, and 5 beside each number. Write the name of the corresponding part. All right, so let's look at the diagram. So 1, that is the stop push button. 2, that is the start push button. 3, that is the contactor coil. And 5, that is the overload. All right, so that's it for part E. Part F, it says explain the function of the part labeled 3. All right, so the part labeled 3, that's the auxiliary R holding contact. So the auxiliary or holding contact closes when the coil is energized to form a holding circuit for the starter or contactor after the start push button has been released. All right, so that's it for this question. All right, so let's move on to the next question. So this is question 10 from the 2012 past paper. Part A, it says give two methods used to effect a reduced voltage at the terminals of a three-phase motor at starting. So the two methods are star delta reduced voltage starter and auto transformer reduced voltage starter. All right, so that's it for part A. For part B, it says give the name of each type of connection shown in figure 13A and figure 13B using labels. All right, so for figure 13A, that is a star connection. For figure 13B, that's a delta connection. All right, so that's it for part B. So let's move on to part C. It says, briefly explain how a star delta motor starter connects the winding in a three-phase motor to obtain a reduced voltage at start and the rated voltage on run. During the startup phase, the starter connects the motor windings in a star configuration, which effectively reduces the voltage across each winding, which in turn reduces the current drawn by the motor. Once the motor has reached a certain speed, the starter switches to delta configuration, which connects the windings in series and provides the motor with the full rated voltage. This then allows the motor to run at its intended speed and power output. All right, so that's it for part C, and that's it for this question.